We've already heard that Avi is the professor of theoretical chemistry at the Hebrew University in Jerusalem. Avi's work initially was on equilibrium statistical mechanics. And if you look at the things he worked on, you'd see things such as chemical reactions, laser chemistry, this sort of thing. And then suddenly there's a phase transition that Avi underwent, at least his work underwent, around 1980. And that's a phase transition which is accompanied by his going to UCLA, to coming to UCLA for 2 years as a visiting professor, when he started to work with Bill Gelbart. And the two of them decided to change areas, to start working on self-assembly. And the kinds of problems they looked at were could be summarized by the title of a book they co-edited with Didier Roux, micelles, membranes, microemulsions, and monolayers. And together, over a period of close to 20 years, they wrote 42 papers on this area. Avi's work then underwent another transition, not quite as sharp. In around the year 2000, he started looking at membranes and DNA, a little before 2000. And this went on to looking at DNA and led to the study of DNA packaging and viruses, work that he's done again with Bill, and some of which you'll hear today. Avi?
Thank you. Is it on? Yes, it is. It's a very special and great pleasure for me to be here, honor to, because as you heard from Chuck, we worked many years together, Bill and I. We are still working together, not the same intensity, but still. And it's really a big honor to be here. I will talk a little bit. It will be a kind of retrospective talk about the work we did together, theory. It's very simple theory. And I picked from here and there, from some papers, from some work, a little bit here, a little bit there, without complicated equations or anything. And just to tell you a story, and I think the story will be simple. Maybe at some point a little bit primitive compared to what we will hear later, but still, it's good. The work was done, what you see here, work was done with Shirley Tzlil. She was my PhD student, and she was also here. And she's now a professor at the Technion, working on intercell communication, doing nice work. All the rest are either postdocs, except Chuck, of course, are either postdocs or students of Bill Gelbart, but all of them, those in bold, spent time with me in Israel. They came for short periods, and it was great fun. So now I changed the title. I wrote modeling, and then Bill suggested from phage to proof. I thought it's nicer. Thank you, Bill. And I'll continue. This was 1980. in the UCLA swimming pool. See, we're both a little younger. That's a book that Chuck mentioned. There are many jokes about it, but I don't have time for that. Before that, Bill and I came. He was in Chicago and then in Berkeley. I was in Jerusalem at Weizmann in Germany. But we had similar background. We worked on molecule light interaction, chemical reactions, non-radiative transitions, and topics like that. Then just before 1980, I wanted to work on biology. My brother is a biologist, and you knew him. And I felt that we have exhausted the traditional questions in some of the traditional questions. I wanted something new. So I spoke with some friends in Jerusalem. I said, what's interesting? They said, well, maybe membranes, they have phase transitions. I said, I like it. I wrote to Bill. He said, shall we work on membranes? And because he already worked on liquid crystals. And there is a liquid crystal into gel transition in membranes. So, yeah, okay, let's work together. So we came in 1980. First I went to I have this tendency to tell long stories. It took us 20 years before we got to membranes, maybe 15, because we worked on self-assembly. And here I jump about 17 years when I think Chuck mentioned that this is DNA, by the way. It doesn't look like, but it is DNA, and it is surrounded by small counter ions. And it's a very interesting phenomenon when you mix DNA with little counter ions with the cationic membranes. These two big macro ions, they bind to each other. They form a complex called lipoplex. Much work was done on it in the group of Cyrus Saffinia in Santa Barbara. And they do it, and that's what is so exciting, they do it by releasing the little ions. They neutralize each other electrostatically. It's very exciting because the little guy go away, and it is an entropic effect. It's the entropy gained by the little counter ions that drive the transition, because they are electrostatically neutralized to begin with. So this is very exciting, and this was kind of among the first time we looked at DNA. And this was the second time that we looked at DNA. I was on sabbatical in New York, 1995, and this friend of mine, Bill, he came, and you know he likes to take it. And that's when I learned first that the DNA is not just a rigid, flexible, semi-flexible rod. It also makes supercoiling. You see, it's supercoiled, and he showed me. He said, Avi, look how exciting it is. And as we did very much in the past, it was in a cafe, Cafe Tachi. Do you know it? No? Okay, I'll tell you about it. Anyway, so this was the beginning of our work on this stuff. Then Bill went for a sabbatical in Paris, and he became a co-author of, well, here is a first author, but here a co-author of a very nice paper where you have viruses, what were they, T5, T7, with DNA, and you put some polyvalent cations in solution, and they inject the receptors that open the tails, and they inject the genomes, and they form a torus. They did it also in a liposome. Here it is in the liposome. Of course, the colors are artificial because it appears on physics today. It was to explain to the physicists what's going on. These are empty, and this is still with the DNA inside. It's the same mechanism, by the way, that they form these torus. It is a counter ion release. You see that they form this bagel. They wouldn't do it because DNA is extremely highly charged. It won't fall on itself. It's only because there are polyvalent cations. Okay. And then came this picture that Bill showed me. He said, Avi, let's do theory for that, because there must be enormous pressure inside this little virus in the capsid. What was it, T2? All this spaghetti, DNA, was packaged in the head of the virus. The pressure must be enormous. And how is it packed, and so on. So we started working on this project. And the questions were, what are the forces and pressures that are involved in packaging this stiff and highly charged DNA into the confines of the capsid? And you know the important fact here, that's DNA. That's from the lab. Ajay is here? No. A postdoc of Bill. What you see here, this is RNA, but I'll get to it later. This is DNA, and this is 60 nanometers, and the persistent length, that the length that DNA folds bend spontaneously is about 50 nanometers. That's called the persistent length. Beyond that, you have to invest energy. So how can you put this big creature, which is now many times the persistent length, into the small capsid. Obviously, one has to know the bending energy of the DNA. We have to know the interaction between neighboring DNA strands. And fortunately, this information was available experimentally. And using this information, we designed a simple theory. We like simple theories. And here is the theory. But first, the experiment. Again, the counter-ion release, but this just to show you in this case that there are measurements of DNA-DNA interaction by the group of Adrian Precision and Don Rao at the NIH by osmotic stress measurements. And they measured in solution with polyvalent cations and monovalent cations. And in both cases, you see this is a logarithmic scale. They measure the pressure as a function of the interaxial distance between neighboring DNA strands, which tend to pack hexagonally. And they find that in both cases, at around 28 angstrom, very strong repulsion begins. That's a case of no polyvalent. But even if you have polyvalent cations at 28 angstrom, the pressure may go to about 100 atmosphere. It's a lot. And in parallel experiments, a little later, that's by Nick Hudd, you see how nice a torus is formed. That's only with polyvalent cations. Or this one was done in the group of Hansma in Santa Barbara years ago. You see a torus. And the distance, you can calculate the distance, the interaxial distance between neighboring strands. It's 2.8 nanometers. 2.8 angstroms. Thank you. 2.8 angstroms. Fix it. Now, here comes. Pressure is nice, but sometimes to do a theory, we need energy. How do you get the energy? You integrate the pressure, right? I used to teach here in 98. I taught 110A for 2 years, 113A2, but 110A. So the osmotic pressure is the derivative of the free energy. You integrate the pressure, you get the free energy. So we integrate the pressure, we get the free energy. Here we have curves. That's in the absence of polyvalent, that's in the presence of polyvalent cations. And you see that the 28 angstrom, that's the right unit, strong repulsion sets in. This was done by Shelley Tzlil, my student, and in parallel, Rob Phillips, they also did similar work. So remember, 2.8 angstrom, that's the optimal or minimal, also the equilibrium distance, if you want, in the case of polyvalent.
28 angstroms, 2.8 nanometers.
Whatever. I don't remember what I said, Bill. Okay, now suppose you remember the torus. This is the torus. You want to package it into a capsid. You try to do that, but look what happens. That's the only animation I did. It doesn't fit in the capsid. It cannot go in. It's too big. Suppose you chop it like cigarettes in a box, and you pack it hexagonally, and you want to put it. Won't go either. And that's the maximum. That's with 2.8 angstrom. It's again the same error, I guess. So you do a calculation. I had a slide with some numbers and calculations. It was nice, but I took it out because in view of the time. But I'm telling you, you can do the calculation. You know the capsid diameter. You know the volume. You know the volume, the bare volume of DNA. You can calculate how much volume it takes if you package it with 2.8 angstrom distance. And it turns out that you cannot do it with 2.8, but you have to go, it's 2.5, I'm sorry, I don't know what happened.
You got it written right there.
Huh?
It's correct.
Bill misled
That's correct. Angstrom's, yeah, he misled you. Misled me, and you too. I'm sorry. Okay, let's go. Yeah, sure. Bill, please. Okay, so let's see. Indeed, there are measurements, earlier measurements, and they show that the DNA distance is less than the 28 angstrom. The bare diameter of DNA is 20 angstrom. But it is very dense, of course. We also know, we heard about the shape. It is packed like a spool. It starts like a torus inside, depends. And then it goes to a spool when it is a high density. That's a cross section. So it's about 25. How am I doing with the time? You're supposed to show. No, this I don't know this stuff. No, I need it big.
You have 20 minutes.
20 minutes, that's it? Okay. Okay, here is the theory. The theory is very simple, if I skip all the equations. But basically, what we do is you take the DNA, you say part of it is that's a theory for the ejection of the DNA or the packaging of the DNA. So you have part of it in the capsid, part of it outside the capsid. The free energy, or the energy if you want, is the sum of the free energies of the DNA in and out. And there are two major contributions to this free energy. One of them is the bending. You have to bend, and as you put more and more DNA into the capsid, you have to pay more in energy. And then when they get near each other and you go below the 28 angstrom, there is a very strong repulsion. So these are the two contributions. You add them. That's the length in, that's the length out, and you do some calculation. And look what you get. You get what you see here, that this is a force. This is a force. This is the free energy. We also calculate the force. And you see that this is the size of the DNA inside, the length inside. It is in units of the persistent length. There are in lambda 350 persistent lengths that you can package into the capsid. And you see it shoots up very strongly. The main contribution to the energy is the packaging, is a repulsion between the neighboring DNA. And this is because the bending pushes them. The bending, when you go to the small radii inside, pushes the DNA outside. At the same time, and independently of what we did, there were measurements in the group of Bustamante by Doug Smith and others, single molecule measurements of the force required from the motor protein to package the DNA. And they got, this was the original one, and this is a corrected one. Several years later, better measurements. And if you can see, first of all, the profile is the same as we predicted independently. Even the numbers are similar. We got like 50 piconewtons. They got like 50 piconewtons or 30 piconewtons. They were excellent agreement to begin with. Very simple theory. And I'm not surprised because what is there? You have the bending that we know, and you have the repulsion that we know. And it's not surprising that you have good agreement. Then came a young French scientist and said, what happens if you put some osmolyte, PEG, in solution? You increase the osmotic pressure in solution, maybe it can inhibit the ejection of the DNA. I thought it's nonsense. But Bill said, let's try it. So we added to the free energy a PV term. That's the pressure related to the reflecting the stress on the DNA that is ejected. I thought it's nonsense because the pressure is so high that the DNA is ejected in a very strong force. But we found that as you increase the pressure, this is a free energy as a function of the ejected length of the DNA. And above about 3 atmospheres, osmotic pressure, there is a minimum in the free energy, which means the ejection may stop, may be stuck here. Now here comes a very dramatic result that Bill will talk about it. They did experiments. Alex Abilevich, who is here, is Bill and Chuck. And they did the experiments. Beautiful experiment. This line is a theoretical prediction. This is an experiment, and it shows that as you increase the osmotic pressure, you can basically stop the ejection. And this is a phase transition in the life of my friend Bill Gelbart. He became an experimentalist. And in fact,
It was the last time that an experiment worked the first time.
anyway, so that's the end of my story. No, it's not I could go on, because in addition to our simple theory, and motivated, I think, mainly by the work of Bustamante and later by the work done here at UCLA, many people started to do simulations, including our good friend, former postdoc of Bill, Zhengan Wang. Zhengan, are you here? Hi, Zhengan. And beautiful work, finding all kinds of interesting phenomena. But in fact, James Kint, who worked with us, was the first to do the simulations. This is Langevin simulations, but on a PC, he couldn't put all the DNA inside. Anyway, one should be careful with these simulations and their interpretation, but I would love, it could be fun to talk about it, but not now. I will rather switch. Now I have 15 minutes. Oh, that's good. 15 minutes. I feel like a runner. But I'm covering about 15 years. I'll talk now. Then came the time of RNA. At that time I started to be busy with other stuff, but we still did some work on RNA. And we did a lot of work on RNA, on the theory. I mean, a lot of experimental work was done here. Beautiful work. And I should say, I think at this point, the work done here at UCLA in the lab of Bill and Chuck Nobler inspired many, many theoreticians around the world. They just wait for the new result to come hot from the oven and come up with a theory to explain it. Fortunately, I'm close to Bill. I knew first. But not always I could come up with a theory, or I was too slow. In any case, I'll talk now in the last 14 and a half minutes, I will talk about what we did with RNA. RNA, well, the structure is known for short RNAs, but it's less known for long RNAs. But there are mathematical algorithms, RNA-fold, M-fold, to calculate equilibrium structures. Of course, these are models, and they are subject to errors, to calculate the secondary structures. And first thing we know is that RNA in viral capsid is not as highly pressurized as DNA in phages. However, if you calculate, you know, the volumes, etc. I calculated, maybe I'm wrong, that about 50% of the volume, the inner volume of the capsid, is filled with RNA, which is a lot, because the maximum volume close packing volume is about 75%. So that's a lot. So it's highly, and therefore it's not surprising that there should be a correlation between the size of the RNA and the size of the capsid that you can put together. These are, again, measurements done here at UCLA by Ajay Gopal. And you see this is RNA in solution, and when you put it in a capsid, you have to quench it a little. I understand that we will hear today from Professor Zhao exciting results about the structure of the RNA in capsids, and also a nice poster by Christian Bern, student of Bill, and you're of course invited. But I will continue talking about the simple work that we did. Let me see. All of these people are here in the audience. They are from the group here at UCLA. Beautiful work again. And you see they took RNA of different lengths. Say you take 3,000, which is about the size of CCMV RNA, and it packaged nicely into one capsid. If you take 6,000, no room, 2 capsids, fused. It goes as you expected. If you go to 9,000, then you need 3. If you go to 5,000, you have 4. It's beautiful. It shows a correlation exists. And now the simple theory we did. First guy to do it, Aaron Joffe. I think I saw him. Hi, Aaron. The people in dark blue here spent time with me in Jerusalem. It was a great pleasure. And the measure that we used for the secondary structure of the RNA was suggested by Ben-Shaul and Hua. It's called the maximum ladder distance. It's basically the longest distance from one hairpin to the other, measured in units of base pair rungs. So that's a maximum ladder distance, right? So this, if you want a 2D measure of the size, and if you compare viral RNAs to non-viral RNA, you see that the MLD, the maximum ladder distance of the viral RNA, is very significantly smaller, 200 base pairs along this path versus 350 along this one. This one is random RNA. Random RNA means you take the sequence of the RNA, you scramble it, you randomize it, and you put the result again into M-fold or RNA fold. You calculate the structure, and you calculate the MLD. So this is what I call random RNA. It's random sequence RNA. Aaron did it for many, many, many viruses. And this is the MLD versus the sequence length. These are viruses, except this one, the Obama virus, which is not icosahedral. All of them lie below this line, which is a line of random DNA. So they are more compact, considerably more compact. Random DNA, you can say it's irrelevant biologically, and you're right, but it's fun for theoreticians because you can think about it. And the slope of this line is 2/3. We say that the MLD, or the average MLD, scales like n, the length, to the power of 2/3. Physicists like powers a lot, and power laws. We also like them. This is a beautiful work done after our work by the group of Rudi Podgornik. What they did, they took the viral sequence, and what they did are synonymous mutations. I will not start to explain what a synonymous mutation is, but basically the sequence, the genome, in principle, it is the same genome, but the fold may be different. And they found that if you take the viral genome and you do a synonymous mutation, you don't change you change the sequence. You replace some codons by other codons, but you don't change see what I mean? You change the codons, but you would get the same protein from it. they behave like random RNA. So there is a specific fold for the viral RNA. And if you do either you randomize a sequence or you do synonymous mutation, they behave the same. Okay, now we want to know how much. Boy, this one is running fast.
I'll show you when there are 5 minutes.
What?
I'll show you when there are 5 minutes left. I'll show you when there are 5 minutes.
Ah, okay, good. So it's not yet. I can take a sip of water. So how do we go from 2D to 3D? There are two options. One of them is take the MLD. Here. Take the MLD. Say, ignore the branches. And say, treat it as a linear polymer. When you have a linear polymer and you want to know the linear polymer scale like the length to the power of 1/2. But I'm sorry. The 3D size of a linear polymer. So we take this as a linear polymer, and we take the square root of it, as if it was a linear polymer. Now remember, the MLD scales like 2/3, which suggests that the radius of gyrations, that namely the size, scales like 1/3, which is very different from anything. In particular, it is different from what we call a randomly ideal random branch polymer. It has a branch pattern, but as I'll show you in a second, it's not a randomly branched polymer, the RNA. The other method is you open a book and you see that there is an alternative way to calculate the radius of gyration of an ideal polymer, branch or not. It's due to Kramers, and the calculation is very simple. You take the branch polymer. First of all, we map the RNA to so-called tree graph. We treat all loops as vertices, all duplexes as stems. Very crude approximation, but it works nicely. And then you look at all divisions of this polymer into two parts. You multiply the number here by the number here. You sum, you average, you get the radius of gyration. This is the work done by Li Tai Fang. He's also here. And it doesn't matter which way you do it, the same result. Whether you do the square root of the MLD or you do Kramers, you get the same result. All the viruses lie below the random RNA curve. By the way, we also showed that the number of nucleotides and the number of loops scale, they are proportional to one another. I mean, the number of loops is growing linearly with the number of nucleotides. This is also from the work of Aaron. He showed that the MLDs and that's for RGs of viral and non-viral are not very different. Sorry, not the MLD, I'm sorry. They are very different. But their mean duplex lengths, about 5 base pairs, are similar. The distribution of duplex lengths are the same. The pairing fraction, about 60% of the nucleotides are paired. The bases are paired. And the minimum free energies are also similar. So where comes the difference? We wondered where the difference comes. But first, we did some work with Li Tai. We had a model, very simple model. We called it a sequential folding model of the RNA. It goes like this. You take the RNA, you look for the longest duplex, you form the duplex, you have 2 daughter loops, you repeat it, you end up. We called it the SFM. Turns out it explains very nicely the average duplex length, which is 5, the pairing fraction, which is 65, and this is analytically. Numerically, we also found that this SFM also predicts the n 2/3 scaling. Even the structures that you get from this simple model looks reasonable. But still, there were questions. Where is the difference between random and viral RNA? And the conclusions we had is that it must be something in the branching pattern. What I mean by branching pattern is look here now on a simple polymer. This is highly branched. This is linear. A branched polymer, branched RNA is anywhere in the middle. So Aaron and Ajay analyzed many sequences of viral and non-viral RNA, and they found that viral RNAs have a higher fraction of high-order loops. That is, high-order vertices. If you look here, these are the high orders, the ones that lead to more than 3 duplexes. And then, so RNA appears as a branched polymer, but random sequence RNA scale is n to the 2/3, RG n to the 1/3, but this is less compact than viral RNA. What about ideal randomly branched polymer? Take a polymer, not RNA. It's different. Ideal randomly branched polymer has a scaling of n to the 4th. It's not, there are long proofs of that, there are short proof of that. So this means that the randomly branched RNA, randomly branched polymer, in all cases you ignore extruded volume effects. We talk about ideal system, is more compact than random sequence RNA. How does it compare to viral RNA? What we did here, this is, by the way, a randomly branched polymer. You take an example. Take a trimer here, a dimer here, at given proportion, and you start sticking them together, you get a random polymer. All random polymers show this behavior. And the question is, why 3 graphs of random RNA differ from ideal randomly branched polymer? Is it in the vertex degree distribution? Well, it's not. Look at this tree and this tree, they look very different. What I'm telling you, they all have 1, 2, 3, 4, threefold vertices. Here the same. They have the same vertex degree distribution, they look different. What we did now, 1 minute. What we did now is something very smart, very nice. It was suggested by Ajay and taken over by Walter Singaram, who is not only visited me in Jerusalem, he now is in Jerusalem because he married an Israeli girl and now they have a baby and he doesn't want to go back. Otherwise he would be here. He sends regards. Anyway, so now we did something very elegant. I may steal another minute, but not much more. And this is a very elegant, now I go to the field of physics games or mathematics games. It's called the proofer procedure. Take RNA, map it into a tree graph, and now you can map this tree graph. There is a trick here, I don't have time for that, but it's very simple. You pluck one leaf at a time, and then you end up with a sequence. It's called the proofer sequence. There is one-to-one correlation between the tree, namely between the polymer and the sequence. You can also go back. Now, you can take the sequence. That's numerically very convenient. Instead of plotting graphs and working on them, you take the sequence, you scramble it, you shuffle, you do proofer shuffle. When you proofer shuffle, you change the structure, but you don't change the distribution of vertices. They are the same here and here. If you feel like, you have to believe me. So what we did is, the question was, what happens when you do it to viral RNA, when you do the proofer shuffling? What happens when you do it to a randomly branched polymer? And when you do it to a viral, when you do it to a randomly branched polymer, you find that the RNA, the random RNA, which scales at 1/3, remember, becomes a randomly branched polymer which scales as 1/4. That's very significant mathematically. It shows that it is not as compact. This is a scaling. You see it is plotted the radius of gyration as a function of the length to the 1/4. It's linear. These are different methods of calculation. And that's one before last. You take the viral RNA. I took the numbers for CCMV here. And you can do, for example, you can randomize the sequence, or you do synonymous mutation, as I told you about. And you see that the MLD, or the radius of gyration, goes from 6.1, that is in unit of duplexes, to 8.4. It is bigger. That's more compact. If you take this one and you Puffer shuffle it, remember Puffer shuffling, we change the structure, but we don't change the number of vertices of order 3, etc. Again, you get a randomly branched polymer. It is somewhat less compact. You take the randomly branched, the random RNA, random sequence RNA, and you Puffer shuffle it, you get the randomly branched polymer. It's all very interesting, mainly for a mathematician whom I met in Jerusalem, a very good mathematician. And he was so excited that we used Puffer because he worked on it in his PhD that now he wants to understand many things related. That's my last. There are many remaining questions. First of all, how relevant are the equilibrium predictions of M-fold and RNA fold? Are they equilibrium structures? It's not obvious. The RNA is equilibrium structure. How fast is the kinetics of transition between the many close-lying structures? Is the secondary structure of RNA preserved during viral assembly? Maybe now with the new measurements and what we will hear and see in the poster, we know a little more, but it will take time. We didn't ask what is the role of absolute volume in all this. And mainly for mathematical and theoretical physicists, we still struggle to explain why MLD scales is n to the 2/3 for RNA, random RNA. And here is my last one, and this is for you, Bill. I wish you many more years of happy personal life and creative science, and of course, a little bit of luck, especially with those replicons. And if you know Bill, wow, I had a virus here too. It disappeared. Anyway, that's one of his grandsons, and Bill, like, he loves kids, he loves flowers, and he loves nicely behaving viruses. And I think I'm done. Thank you.